In this video, we're going to look at one organ system that people often ignore as an organ system, and that is the skin, or more formally, the integumentary system. So the skin itself is an organ and has multiple features such as hair, sweat glands, the breast, and others that allow it to do its work. And we're going to investigate a few of those, but to see what they do and how they do it, we're going to look at them microscopically. Now that we're looking at the skin in a microscopic view, we can see we have an example here of what's called thick skin. And we can see three layers here fairly readily: the epidermis, the outer layer of skin, the dermis, which contains blood vessels, glands, and so forth, and the hypodermis. Now the epidermis is largely made of keratinocytes. We have melanocytes for pigmentation in there as well, along with some antigen-presenting cells that help us fight off any pathogens that are coming from the outside, but the keratinocytes are largely able to do their job because they multiply down here at their basal level and die, producing a lot of keratin as they do so, making a watertight barrier with the outside. The dermis contains blood vessels and also a great deal of dense irregular connective tissue, nerves in there as well. And then the hypodermis is not exclusively made of fat cells, but there tend to be quite a few adipocytes or fat cells in it. If we take a closer look at the epidermis here, we can see this outer layer. This is the epidermis, and all of these cells are coming from this basal layer right here. So they're replicated along this basal layer, and they push the cells outward, and as they do so, they make keratin, they die and become flattened, and this is going to be the outer surface of our skin. Thin skin looks very much the same. It's just that the proportions, or the proportional depth of the epidermis is going to be a little bit different. So we can see the epidermis there, dermis here, and we just happen to have quite a bit of hypodermis here, along with some signaling organs right here like Pacini and corpuscles. That's just for fun. And a little closer look here, we can see once again epidermis and dermis there. And one thing we can see for sure here are some of our first epidermal derivatives, or structures that are arising from the epiderm and migrate into the dermis or even deeper to get their job done. So these are sweat glands, more properly known as eccrine sweat glands. These release a watery fluid that's going to allow us to actually release it onto pores onto the surface, which will then cool the body off. The sweat gland ducts, one single duct for each one of these little coiled structures here, reaches all the way to the surface. So let's take a look at this in a little bit of a cartoon view. We have our epidermis there and the dermis. Early on, during developmental life, we have an epidermal bud extend into the dermis, and it forms this coiled structure as it stretches downward, and that coiled structure will eventually open up, have a hollow lumen there, and that's going to be where these secretory cells release their watery fluid. There's actually also some myoepithelial cells or contractile cells that help squeeze it out, and that pushes the fluid all the way up the coil to the pore opening on the outside of the skin. Now something very similar happens when we have hair follicles form. So right here we can see we have a hair peg going into the dermis like we saw before, but in this case it's going to have a little bit of a bell shape, and we're going to have vessels coordinate with each other to actually go in here and form this what's called a hair papilla. So the hair is remaining connected to the outside. We have the development of a sebaceous gland here, but the important thing is to remember these are keratinocytes. So these would be producing those keratin cells, but instead, fed by the vessels at the hair papilla, some nerves as well, these keratinocytes make hair. So this is going to be dead keratinocytes, but instead of into a flat sheet of skin, it gets wrapped up into a mostly ovoid or roundish structure, the hair. So we have the root of the hair consolidating up as it goes out the follicle there. Sebaceous glands are nearby to release kind of a greasy fluid, kind of a fluid into the hair follicle to keep it from getting kind of dangerously fragile or ready to snap. And we also have muscles, smooth muscle associated with it, which is what allows us to have our hair stand on end when we get scared by something. But once again, these keratinocytes moving into the dermis are what actually create the hair, and the hair is just modified skin. And the hair grows up and out, will eventually crack, break off, and the hair will then regrow down here. So let's take a look at that in a little bit of a microscopic view, we'll zoom in on a single hair follicle here, and because it's not a cartoon, the plane of section doesn't catch the hair follicle perfectly on the way out, but we can see the papilla here where vessels are coming in. The keratinocytes are lining this bell-shaped area and releasing themselves and forming the hair follicle at the root of the hair and then moving up the shaft of the hair itself. Note that we have the sebaceous gland cells here emptying into the shaft and coating the hair on its way out. And just for kicks, we've got some eccrine sweat glands in the same area. Now, fingernails and toenails are really just modified hair. And first off, I apologize for the coloration here. I tried to draw more natural looking fingers and toenails, and it just came out looking way more disturbing than this. So we're going to stick with blue and purple for keratinocytes and this slightly golden brown for the actual hair itself. Although if your toenails and fingernails are this color, might be a sign of something you need to get checked out. Anyhow, we have the nail fold here at the top, what we call our cuticle, and we have the keratinocytes making kind of a cup around here. Now there are other structures that help to anchor the nail plate in place both above and below, but the nail plate itself is going to be the keratinocytes produced here, pushing themselves out, and they form kind of a soft keratin at first that gets harder as it grows out. So the nail is really a lot like individual hair cells compressed together, pushed together into a plate rather than as individual follicles moving their way out. Now, this is also going to be how animals develop their talons, their claws, and so forth. And one of my favorite fun facts is that a rhinoceros horn is just keratin bundled together. So this can actually be quite a bit harder than you might think hair could possibly be. But that's the power of all those little keratinocytes bundling together. Now, believe it or not, teeth are derived in a very similar way to hair and these sweat glands. So along the developing jaw, the maxilla, and the mandible, we have kind of a dental lamina, an area where teeth are prone to develop. And as that happens, we have the epidermis invade the underlying dermis, making another one of these bell-shaped buds, but in this case it is a tooth bud. And it's going to remain attached to the outside for a little while by something called a dental lamina. But just as the other epidermal derivatives often would associate with some area of the dermis for vasculature and nerves, we have this area, the dental pulp, feeding the developing tooth. And the dental lamina is connecting it to the outside, at least for now, and we have the bud of a permanent tooth developing here as well. So what we're looking at here, this bigger structure, is actually our deciduous or youth tooth. That's going to be the one we have as a child that eventually gets lost, whereas the permanent tooth actually develops off of that lamina. Now, as development proceeds, the connection to the lamina gets more and more tenuous, and this bell-shaped structure forms what's known as the enamel organ, and that's going to make the mineralized tissues of the tooth. The bud of the permanent tooth will do the same thing, but it develops a little bit more slowly, and it's going to branch off the dental lamina and migrate more inferiorly, where it will keep growing and eventually displace the deciduous tooth. But the deciduous tooth is still growing inside the jaw. It's disconnected from its dental lamina, but it's going to be forming the enamel on the top part here, the hardest naturally occurring mineralized structure in the body. We're going to have enamel-producing cells there. Don't worry about it, but they're called ameloblasts. And we've got dentin making up a large portion of the tooth. It is also a mineralized tissue, just not quite as strong as enamel, and it's produced by cells underlying here. Now they're called odontoblasts, but once again, I'm not going to make a big deal out of knowing that. Just be aware that they do have names for each of their functions there. We can see this developing tooth for real in this histologic specimen. But real quick, before we go there, I just want to note this growth is occurring and the tooth will eventually erupt out from the epidermis here and actually stick outward, and the enamel will form the top part of the crown that covers it. And once that tooth is erupted, we can't make any more enamel because there's no more cells surrounding it, coating it, that can create the enamel, and so we've pretty much got all the enamel we'll ever have when this tooth erupts. All right, back to the developing tooth here in the mandible. We can see the tooth just there, and One thing to be sure about is my picture a moment ago is certainly not to scale. It was trying to get some points across, but you can see how extensive the dental pulp is here, feeding this developing tooth. Now, the mature tooth will have very small amount of dental pulp in its root, but it will be surrounding it, but it develops from this large cluster of cells in the dermis, which is then going to be surrounded by the developing jaw. So in this case, the mandible or the maxilla. Taking a very big close-up here, we've got the enamel forming on the outside with those ameloblasts there, dentin just inside of it with the odontoblasts and their tubules feeding the dentin right there, and then our dental pulp. All right, in the earlier illustration, we basically showed how a tooth can form with a single root and papilla at the core being supplied by blood, and the various teeth have different shapes, and some of them have more than one root. So the development can be a little more complex with multiple roots developing in some of the further back teeth. We're not going to worry about the individual distinctions between all of them, but you should know that as an adult we have two incisors, which are relatively flat, good for chomping. We have a canine, single canine on each side, and that's going to be good for gripping. Then we have two premolars and two molars. We often have a third molar, known as the wisdom tooth, that either fails to come in or is removed if there's not enough room in the jaw to accommodate it. Well, it may not seem like it, the breast is actually derived from a sweat gland. So the sweat glands that form all over the body can form the breast as well if they're in an area known as the mammary line, which extends all the way down the lateral side of one side of the body. Unlike regular sweat glands, the eccrine sweat glands, the breast branches multiple times and has one exit point at the nipple. Develop off a primary bud, but instead of stretching down into the dermis as a single coil, we have multiple secondary buds branch off of it and expand into the dermis, eventually forming what are known as lactiferous ducts. Now, these ducts are not going to be constantly active. Instead, they are only going to continue developing to their full mature potential at puberty, and the hormonal signals they receive during pregnancy will actually cause them to become more active and expand. So even though these lactiferous ducts are present in people who are not lactating, they tend to be fairly small, they're not terribly active, and they're waiting for hormonal signals to kick it into high gear. And just so you can see an example of that, we have some breast tissue here histologically, not lactating, so we've got these lactiferous ducts hanging out in a lot of connective tissue. So we can see this connective tissue here, pardon me. So we can see this connective tissue here. We've got some adipocytes here as well. Then we take a look at active lactating breast tissue, and you can see pretty much everything we see in here is going to be those lactiferous ducts having expanded, become more active. They're releasing milk into their lumen, and the connective tissue that's anchoring the breast to the skin, this is called a suspensory ligament or ligament of Cooper. And we can also see, in addition to the individual lactiferous duct lumens here, larger ducts that are going to collect the milk and take it towards the nipple. Externally, the breast has a central nipple where the lactiferous ducts can open up, as well as a surrounding area called the areola. And if we open up and look at the internal anatomy, this is representing a non-lactating breast. So what we can see is that there are multiple branched lobules that all come together towards the nipple right here that are going to be creating milk potentially. So these glands exist even if they're not actively in the process of lactating or creating milk. There's going to be a variable amount of adipose tissue mixed in as well as connective tissue known as suspensory ligaments of the breast that are going to be present in between the glandular tissue and going out to the surface of the skin. Note real quick that we also have the pectoralis major muscle here, and typically there's what's known as a retromammary bursa, or a space between the breast itself and the pectoralis major. This model similarly shows a lactating breast, which has enlarged due to the enlargement of the glandular tissue therein. The nipple is more prominent, as is the areola, which often increases in size. If we take a look inside, This model is doing a pretty good job of representing the increase in actual glandular tissue that's secreting the milk going through the lactiferous ducts to empty at the lactiferous sinus and then the nipple. The fat may be a little less prominent here, but we can definitely see the connective tissue of the suspensory ligaments of the breast a little more clearly here, as we can also see still pectoralis major here and the retromammary bursa that would be located between the two. At this point, if you have been following this short course in anatomy, may not seem that short, but if you've been following the introductory anatomy course I've laid out, this is the last talk. So congratulations, you made it to the end, and very appropriately for talking about skin derivation, I'd like to send you all off with a quote from one of the faculty who taught at my institution, Dr. Bill Martin. You can always consider anatomy to be the study of the skin and everything inside of it. I hope you all have a great day. Thank you.